Thank you, Marie-Paule, for the introduction, and thank you, Spike, for an amazing, inspiring talk. I think I will actually have a way of connecting our both talks, because I think basically all of us are going to talk about similar subjects. So I am from the Interdisciplinary Center in Israel, and I've been involved in computer graphics ever since I did my PhD in Israel. And then I spent some time in Texas at the University of Austin. And I have numerous collaborators in various places, and the work I'm going to show here is, of course, a lot also based on all of those collaborations. And I'm going to talk a little bit exactly about the type of tools that we've been introduced to in the previous talk, and more specifically, how to combine maybe the human and the computer together to create something new. So basically combining human interaction with computation. Let me start with a very simple example. Here's when we talk about creative tasks, obviously one of the first things that people think about is drawing portraits, right? So here's an image, and there are two drawings of that image as portraits here. And let me ask you, can you guess which one of those portraits was done by a computer and which one was done by a human being? So let's say who says that the right one is a human? Okay, so most of you think that the right one is a computer. Or you don't have any opinion, I guess. Anyway, so the right one is actually done by a human, and the left one is done by a computer. And this is basically a work that I'm not going to talk about, because this work is an automatic way of creating portraits by a computer. So I'm just going to describe shortly the way that we go about doing this. First of all, taking an image, you extract the edges, as John was telling us. You know, edges are a very important cue for people to recognize what's going on in a scene or in an image. We do have some shape deformation. We don't take the exact edges, but we do deform the image a little bit, and we do it also according to specific artists. So what we did in that work was basically take a specific style of an artist and try to imitate it by a computer program. And then we create some curve generation. So instead of just looking at the pixel, we're actually converting them to stroke, again, just by a similar way that John was talking about. And then we replace those curves with strokes of the artist. And that's why it looks more or less like a human drew this specific image. The problem in this approach, obviously, is that there's no user in the loop. There's no human in the loop. This is sort of an automatic way of creating images that imitate what a human being would draw. And what I wanted to talk about is really how people can use the computer as a tool to create art or to create design objects. Of course, the simple way to do this is do it yourself, right? So people have been using various mediums to create art, to create designs throughout history. But in this case, there's no computer in the loop, right? So this is the normal or the original way of doing things. And what we're interested, or at least I'm interested in, is the combination, right? So we have two options. Either draw me a sheep sort of things, right? Basically tell the computer to do it, and he will do it for us. And this is a fully automatic method. And do it yourself is basically all manual, right? So we do it ourselves. We don't consult the computer anyhow. What I'm going to talk about is really the middle place here, is using the computer as a tool to create stuff. And of course, there's many programs these days to create both images, photographs, animations, 3D objects, and various things. And they usually look like this, right? So you have these amazing programs that can do amazing stuff. You can see them in motion pictures. You can see them, in art. I see a small problem with this, because these types of tools usually they're a bit complicated, right? So when you talk about someone who wants to be creative, who wants to create stuff, I think this is not really the way that people want to deal with creative objects, right, or creative doing, right? So these are control panels with many, sophisticated functions that can change the way things look or the way things, shape, but they don't really inspire creativity. And what I was more interested is really to make maybe simpler tools, right? Because everyone knows that simple is beautiful, right? But when I say simple, the question is, what do I mean by simple, right? So can it be simple for a different audience or for different users, right? It could be simple for professional designers and artists, right? So maybe talk in the language of artistic design. Or maybe I'm going to talk about simple for non-professionals, right? So the tools should be simple that even a non-artist could make something creative. Why not? And again, you were mentioning this nice kids program to create art. But the funny thing is I'm going to talk also about some other notion of simplicity, and that's actually I believe that there's still a difference between humans and computer, and some things are simple for humans and difficult for computers, and some things are difficult for humans and simple for computers. And what I'm going to talk about really is many things that really lie in the middle there, right? And the thing that I'm going to talk about is how to make it simple for everyone in the process, also for computers, not just for humans. So I'll start with an example. And what you can see here is an interface for sketching something. And by the way that you'll see that the sketch is going on, you immediately recognize this is not an artist, right? So this is just someone very simple who's trying to sketch something, very crude. And the interesting thing here is that once we have this sketch, okay, someone is trying to sketch some scene, and what we get is a very crude sketch of what was in the mind of the person who sketched it. And this is a very simple tool that almost anyone can use, of course. And then we get this sketch. And what we were trying to do is convert this to a real image, right? So maybe I'm trying to sketch some image I have in my mind, and then we convert it to an image, right? So if you don't like this specific image, you can, of course, take the same sketch and maybe create a different image. That's, again, not real image, but it didn't appear in reality, but we can create it using sketching. So this is called sketch to photo, and you can create various types of sketches. Here's a more romantic one, and then you can create a real, image of that specific sketch, or yet another one, the same sketch, maybe different image. If you don't like this one, maybe we create a different image yet again. So the idea of this project was really, we're in the realm of collages, right? So everyone has done this, I think, in kindergarten or maybe at school. So you take a bunch of things, you cut them out, and then you stick them back together to make those types of artwork. And what we were trying to do is create really a tool for people to create those types of collages, but create a more realistic thing, right? So what we do is we do the same thing. We find, cut and paste those elements, and you can see here the original images where these elements come from, and then we paste them back, again, using the computer to create the final image, which is, again, not a real image, but something that someone had in his own mind. So the input is a fairly crude sketch. The output is a, let's say, rather photorealistic image. It's not exactly, but, sometimes it's better, sometimes it's worse. So how do we actually accomplish this? There are various techniques needed when we talk about the algorithm or the computer. So first of all, you have to have an image search, right? So we search for various elements that you incorporated in your sketch. You need to find them. Then you need to segment them out of those original image, and then you need to composite them back into a new image, right? So all these are maybe problems or difficult problems that computer vision and computer graphics have been dealing with, and there are a lot of previous work, too many to mention, that deal with all of those problems, and they are difficult problems, right? They're not simple to solve, especially in a general case, as you can see in this example, how do I cut out the boat out of this image and composite it back into a new composition? Now, the idea that we had is, in fact, trying to make this simpler problem for the algorithm, not really for the humans. I mean, the humans just draw something, and the algorithm needs to solve all the, greedy details. So what's going on is that we're actually trying to make it simpler for the computer by using simpler images, right? So how do we know that an image is simple? For example, if we segment it and there are not too many segments in the image, right? So that's a way sort of to measure why or if the image is complex or simple. And then when the image is simpler, it's easier to segment out the main object, again, by maybe looking at the saliency of things in the image and finding the center object and cutting it out of the background, and then compositing back. How do we find images? Well, I don't know if you noticed, but the user didn't just draw the things. He also added some text saying or describing what he meant to draw, because, frankly, if you look at the drawing, sometimes you don't recognize what's on there. So you need some text to understand. But not only us, also the computer. So what we do is we take the tags from those simple sketches and we look for images of a sailboat, for example, in this case. And as you know, the internet is full of those types of images. But the problem is that most of them are very difficult. And so the idea here was to try and find automatically a way to filter out difficult images. And as I told you, we do various steps of filtering. And then we are left with just simple images that we can cut out the pieces and then paste them back into a new composition. So there's a collaboration going on here between the human and the computer. The human does the sketches, as I've told you, but he or she also puts the tags or the text for the images, so we know what to search for. He also does the composition, right? So the human actually positions the elements on the image, so there's no need for a composition to be going on by the computer. And then sometimes there's also some corrections going on in post-processing to produce the results that you've seen. The important thing to remember here is that there's no need for exactness or tedious process of positioning or drawing very accurately, right? So you've seen a very crude sketch turns into a very realistic image. So that's the human part. The computer part in this case is, first of all, search for the images. That's easy to do for computers. Filtering them out. And again, this is an algorithmic step that we run behind the scene. Segmenting the images that are simple now, and then compositing them back together in a photorealistic manner. And that's, again, there are various works that do all these types of things. The important thing here is that the computer does not need to solve any complex segmentation or recognition problem because of the input that was produced by the user. So in some sense, this collaboration is sort of perfectly matching the two things, right? The key point is that you take a difficult task and you separate it to two collaborations, right? Computers can enhance the creative, abilities of human. They're fast, they're efficient, they're accurate, right? So everyone wants to use computers, but there are still some things that we are better at, and these are mostly semantical things, right? Recognizing what's in the picture, or creating a right composition, or thinking about what we want to produce or create. So all those things are more human-like, let's say, and that's the various examples I'm going to show you follow exactly this specific line, how to use collaboration between these two components of humans and computers. Of course, it's not always a success, right? So you can see this, and this is the image produced, not very nice. And it also takes time, right? So to search for the images and to filter them out and then segment them and rank them and everything takes a few hours for a single image, right, to be created. So hopefully maybe in a few years it'll be fast, so you could do a real-time sketch to photo creation. But for now it takes a little while. So we created images from sketches. Of course, the next step following the seminar is maybe creating 3D objects, right? So can we start with a sketch and go to 3D? I think a lot of my colleagues today are going to talk exactly about these types of things. I'm going to show a very simple work that we've done. Basically, 3D modeling is an extremely difficult task, even for experts, right? So when you talk about how to create those 3D models, you have to be an expert in a modeling system, in a computer program, more or less. Sketching, of course, is much easier. And even if you talk about these very crude objects, it's difficult to create those in a 3D modeler. But if you just sketch something, I think most people can more or less, again, you see this is not made by an artist, by just anyone, create a three-dimensional sketch of an object. And then the question is, can computer help us to convert this type of sketch to a 3D model, right? And yet again, doing this fully automatically, basically taking the sketch and creating a program that will automatically create the three-dimensional model is difficult. It involves perception. It involves, as you'll see in a minute, segmentation, in this case of the three-dimensional object. And these tasks are hard for computers. So yet again, we turn to the other side and think, okay, so how can human make this problem a little easier for a computer to solve? The challenges that are involved in this task is, first of all, interpretation. So you see there are many lines in the drawings, and some of them are silhouette lines, and some of them are internal lines, right? So how do we recognize or divide the sketch to these two types of lines? Then, as I told you, we need to segment the object into different parts and maybe try to model each of those parts separately. We need to position those parts correctly between each other, and we also need to preserve some of the relationships that are evident for a human being. For example, we all can imagine that the top part of this lamp and the handle of this lamp are sort of coaxial. They have the same axis. And just looking at the drawing, it's not necessarily true. So these are the types of relationships that need to be preserved in some sense when we model these three-dimensional objects. And when we go back again to human perception. So when we humans look at objects, we don't really recognize the whole thing at once. Yet again, as Spike was telling us, we look at small details, edges, parts, and compose everything together. And along the way, we also look at the relationships between the different parts, and that's what makes the whole thing, right? That's what makes us recognize what is the specific object that we're looking at. So I'm going to show, hopefully, if it'll work. Oh boy, okay. A demonstration of what's going on in the program. So what you can see here is human modeling a three-dimensional object based on a sketch that was previously created. And what you can see here is a tap. And what the human does is basically finds the right parts or the right model of parts and drags them over to the sketch, and then these parts snap together in a correct manner, creating this three-dimensional object is sort of semi-automatically. So the human only drags the objects and positions them together. Okay, let me close this. So what's going on behind the scene is that we start with an input sketch that a human drew, and then there's some semantic classification of the edges of the sketch, as I told you. Some of them are silhouette edges, some of them are maybe internal. And then the human only drags those primitives from a library of primitives and positions them more or less in the right place. And behind the scene, the computer basically snaps them to fit the specific sketch, but also tries to preserve those, what we call geosemantic snapping, so geometric semantic relations between those different objects. So yet again, the human sketches the parts, so there's no need for someone to, for a program to create three-dimensional objects. It's something that someone has in mind and uses very simple sketching, rough sketching, I would say, to create the object. But the important thing here is that it is sketched using parts, right? So you can see the different parts are drawn separately. Then the human chooses the correct type of primitive, right? So we humans can know that this is a cylinder, this is maybe a sphere, this is a conus, and so different types of primitives someone can drag and assist the computer, assist the program recognize those different parts, but also position them more or less correctly. So you drag and drop them somewhere, and that's sort of a good initial guess for an optimization program to find the correct positioning of those three-dimensional objects, right? And again, you have to remember, there's no need for tedious, precise positioning of two things because the computer basically infers those geometric semantic relations, right? So things that are almost parallel become exact parallel. Things that are almost coaxial become exactly coaxial, and so on and so forth. And these relationships are preserved in the final three-dimensional objects that is created by the computer. So again, you can see the combination of, two participants, the computer running behind the scene, doing things that are exact or difficult to compute, and then the human that actually does this creative and more, rough task of modeling the three-dimensional objects. And here you can see various examples of those sketches and the three-dimensional objects created by them. There are obviously many limitations to this work, right? So first of all, the models are very crude, as you've seen, right? So they're not very exact. They don't contain many details. There's a need for an initial good sketch, right? So we sketched by parts, and not just any sketch can work. It doesn't handle out-of-plane modeling, so something that extrudes towards you or to the back. And there's no textures, and there's a long list of other limitations. So when we move to the next step, the first thing we wanted to do is maybe we can free the user from actually sketching, right? So maybe we can look at, real things and try to model them as they are. And, what better thing to do than to just take a picture of something, right? And this also will allow capturing the textures, the materials maybe, of the specific objects that is modeled, and not just create those gray-looking objects. So the next step is really modeling from 3D images. So we start with a three-dimensional image, and we want to create, again, a tool for a human being to create those objects out of those, two-dimensional images. And here's a small example of a modeling session, in this case of a tap. Suddenly, everything is a tap in my examples. But in this case, you can see that people the human being is modeling the three-dimensional objects, again, by parts. But along the way, what's happening is that those geosemantic relations are preserved, and that means that you can then create or change the way that the tap is looking, duplicate it, change it, and you create something which is more than just a three-dimensional object. It's a three-dimensional object with parts and with relations between those parts. So what are the challenges in this case? First of all, images are much more complex than sketches. As you see, there's a lot of shadows and textures and various parts. The image itself is not made of parts, but it's a whole thing, right? So there's a need somehow to segment it into parts. And in general, you find that there are various, and when you take a picture of something, it doesn't always fit, the great point of direction that you're looking at, the specific object. So what we introduced is what we call the three-sweep approach, and that's basically a very simple, and in this case simple for the user, intuitive way of creating these three-dimensional primitives. And here's how it works. Basically, what you do is you run 3 sweeps. 2 to define the profile, and 1 to define the extrusion of the objects that you want to model. But you don't do it, anywhere in space, but what you do is you do it on an image and sort of copy the elements that are inside the image to create this 3-dimensional object, which is, you can do, as you've seen, rectangular things or circular things, but it's always the same thing. You can have various, changing diameters or also bending axes. And here's the last example. You can see this is modeling a single primitive, right? So this is called 3-sweep, and the modeling, again, this is a tool that assists user create those 3-dimensional primitives and then create more complex objects. So what's going on behind the scene in this case? First of all, we take the image and we convert it into edges, yet again, because what we're trying to do when we fit those 3-dimensional sweeps is we're trying to fit the shape of the 3-dimensional object, and usually the shape is signified by either silhouette edges or internal edges, yet again. So what we do is we extract the edges, and this is, again, a very simple thing to do for computers, a little bit more difficult for humans. What the human does is implicitly separates the objects into parts, because when you model the 3-dimensional object as a whole, you separate it into smaller pieces. And what you can see here is that's basically creating a 3-sweep for each specific component. And when you combine them together, you create the whole object together. So 3-sweep actually models a single primitive, and the human that models the 3-dimensional object can create this or separate this more complex object into simple primitives by using a 3-sweep and a consecutive 3 sweeps to create the different objects. Yet again, in the optimization stage, what's going on is that the computer runs some, exact relations turn into, almost relations turn into exact relations, and these relations are preserved in the 3-dimensional model, and it helps you create, more intelligent models that can then be changed and edited. So the human defines the parts implicitly, as I said, defines the position implicitly because, again, you sweep on the 2-dimensional image, and there's no need for tedious, precise positioning. There's no need for exact drawing, and that makes it simple for humans. What makes it simple for computers, of course, is they define the initial edges, they snap to the primitive because they have a very good initial guess, right? So the human positions the part exactly where it's supposed to be. And the inference of those geometric semantic constraints, again, is something that happens behind the scene and is preserved by the computer. So here you can see, again, some other modeling sessions of complex objects. And you can see that the person can also maybe cut and paste, those things, so they don't need to model each and every part. You can also use, simple mirroring and paste, again, the different parts. And then you can edit the actual object by preserving the relations of the different parts. I'm going to skip the next part. Of course, there are limitations. Not every object can be composed into those nice, cylindrical or cube parts. Here's an example, right? So it'll be very difficult to model such a thing in a 3D sweep. We cannot deal with object, again, that extrude toward us or away from us because we sort of assume that the object is in parallel with the viewing plane. We cannot handle very well non-uniform profiles, objects that are very small, hollow objects, bad edges or shadows, again, produce difficulties for this technique. So obviously it's not, the answer to 3D modeling, but it's a way to make, again, modeling simpler by a combination of humans and computers. And of course, there are still many objects, and you can see some example here, that could be modeled using the 3-sweep approach. Going physical, right? So we want to close the loop and somehow think about things that are not only modeled but also manufactured, right? Printed and things like that. These days there's a whole revolution outside, right? Customized, creation. And there's more challenges here, because when you design things that can really be fabricated, there are other considerations that come into play. First of all, there are many small details in things that are really fabricated compared to things that are virtual. And I'm going to give you an example in a minute. One of the questions is that you create things out of parts. How do you connect those parts together to really fabricate them? And there's a lot of things that involve materials and physics and weights and strength and things like that that are not dealt with in the virtual world. But if you really want to fabricate something, you really need to think about those. So here's an example of a virtual table versus a real table, right? So in a virtual world, everything looks fine as long as it's smooth and it's connecting correctly and it looks okay when you render it, then we're fine. But when you turn into the real world, these legs need to be connected or attached somehow to the tabletop, right? So how do they connect? They're not really created out of one piece, usually. I mean, of course, these days you can print anything in a 3D printer. But, in most cases, I'm not sure you want to print the whole table. But you want to print it by parts. And then these parts need to be connected to each other. So how do you connect them? Well, usually you use screws, and you use holes, and you use welds, and you use, various things that are also important when you think about something that's really fabricable, that you can actually fabricate them. So now there's a whole new realm of things that you need to think about when you model a three-dimensional object. Not only how it looks, not only how it reacts to lights, but also how it actually behaves in reality. Here's an example of a very simple wardrobe with a drawer. How many parts do you think this has? Throw a number. Well, let's say 100, maybe, yeah? Well, actually 300, okay? So there are 300 parts in this object, and usually when you think about this virtually, made out of 15 parts, right? You have doors, you have, top, you have bottom, but when you think about the mechanisms and all the different things that really make this a fabricable object, you need 300 parts. And of course, this is very tedious for a human being to think about all these things when all we want to concentrate on creativity. So what we were trying to do is use sort of an idiom that was used in computer graphics, which is modeling by example, to create fabrication by example. So designers maybe shouldn't really think about all those small details and maybe try to find more inspiration using the program and concentrate on designing and less on all the nitty-gritty details of how do you actually fabricate this thing. And we create a way for humans to model these three-dimensional objects using a database of what we call hierarchical parametric objects. So, and this is called altogether modeling by example. So let's first talk about the database. So the database itself is made by professional engineers, in this case MIT engineering school students, and they were asked to create an object that includes all the parts, including all the gory details and screws and hinges and everything. But then we take that specific design and, again, using a program, we convert it to what we call parametrized object. And here's an example of a parametrized object that can basically change the shape by maybe changing a few parameters in the design. So you can see you can create various different types of objects. And what this example shows that it's not only the size, but sometimes may also discrete things like the number of shelves or the number of brackets or the number of screws. All of this is basically automatically created when someone changes the design. But that's changing as an existing design, right? So when you talk about modeling by example, what someone can do is take an existing design and then change its parameters and create something which is new, but it's not very exciting because it's actually changing a specific design. What we really want to do is take parts of other designs and combine them together to create new designs. And in this case, again, you can see the idea of snapping. Snapping means that a person, when it drags the right object, it puts it in the existing workspace and the thing snaps to position. And that's done, again, by the computer, not by the user. So, again, you don't need a tedious, positioning and exact, finding the right place and finding the right size and so on. But this is sort of done automatically by the program. And these are exactly the same ideas I've been talking about previously. Let me try and... Okay. And the last part is, of course, all these connectors things, right? So when someone draws a drawer into some design, automatically the system brings in all the types of connectors that need to be added to the specific drawer. In this case, when you add a wooden tabletop, you get a specific type of connectors. When you drag a glass tabletop, you get a different set of connectors. And yet again, this is done automatically by the system. In this case, someone dragged the shelf and it was raised a little bit because you need to put spacing for the connectors. Again, this is done automatically. All those details are not part of the designer's designer's job. So here are some modeling examples that were created by various models. So the color here indicates the original model that this piece was taken from. So you can see that you can combine, mix and match various object. And here are some examples that were really fabricated by this system. So once you finalize your modeling, you get what is called the bill of material. And then you can basically run to the store and buy the wood or the glass or whatever you need. And then you can actually fabricate those. And you can see those here, an example. And this is a full modeling session of someone modeling sort of a table. You don't see it yet, but you'll see it in a minute. By taking and dragging different parts into the program. And as you can see, the program also fits the connectors automatically. And then you can then, as I told you, run to the store and find the right things and eventually create the actual objects. Model it. And it holds. Okay. So, yet again, it's a collaboration, as I've shown you, between a human being that actually does the modeling. It uses, given parts. It can't just draw anything, but it has to use those specific parts that are in the database. But this database, of course, could be extended. And the human defines the composition. Again, it's not something that's made automatically, but someone thinks about how to model the specific furniture or other things. It can, human can change the parameters, so basically make things larger or smaller, and automatically the constraints between the different parts are preserved. And it allows the exploration, basically, of various different shapes, which is what we wanted to begin with. We wanted inspiration in some sense, and less, to be exact. There's no need for the tedious, precise positioning or thinking about the connectors. This is sort of done automatically. The computer preserves the relations because the database that we define is really the database of parametric models that include all those constraints between them. The part snaps to each other. So when someone positions something, it doesn't need to be exact. He positions them more or less, and then things snap to place. And of course, it can copy and add those connectors because we have similar things in the database that can be transferred into your new models. So how am I with time? Can I have another example, or should I jump to summary?
You have 3 minutes if you like.
How many?
3 or 4 minutes if you like. But if you want some questions, yes, or even 5 minutes if you don't want too many questions.
Whatever.
Okay, maybe show your example.
Okay, another example. So I talked about static things. I wanted to talk a little bit more also about dynamic things. So, and again, apply the same ideas. So in this case, you have a robot. This is actually an animation. It's not a real robot, but I like the animation because it shows the complexity of movements that can be done even with a very simple robot, right? And when you think about things that are involved in really modeling the motion of the robot, then you know, again, there are numerous ways of defining these, both for animations and for real robots, but they usually look like this, right? So they're complex, you have a control panel, you have functions, you have knobs and knots to change, and that's sort of maybe a little bit against what we call in a creative process, right? So you have to be a very good expert in animation or, you know, robot control to actually create the movement that you want. So in the project I'm going to describe, we thought about, you know, simple things. Of course, not mechanical object or mechanical robots that assemble things, maybe in the future, but we wanted to think about toy robots. So things that are very simple and very fun, and we wanted to make the process of creating or animating a robot as easy as possible. And the idea was what we call mirror puppeteering. Why is it called mirror puppeteering? Because the robot looks at itself in the mirror, in some sense, and does a bunch of calibration steps that are, you know, maybe difficult for a human to do. And here you can see a video of the robot calibrating itself. So this is like a closed loop. The robot is looking at a very simple computer that has a camera. And of course, he has those markers, those, you know, black dots that you can see. And he knows how to follow those markers. And he moves all his limbs and basically finds the positions of the markers and creates a map between those markers to the movement of the limbs. And that's a calibration step. So that's sort of a must in our case. And by the way, this can also be done in a pre-processing step, right? So if you position your robot in a specific place next to your computer, maybe this is done already for you. But you can also press a button and the robot will look itself in the mirror and calibrate itself. Why is it good? Well, because after calibration, the human can come and basically, you know, directly manipulate the limbs and create those animations just simply by doing them, by changing the positions of the limbs, changing the position of the head, overlaying maybe various movements together, and then pressing the play button, and the movement is created. And as you can see here, we were doing some experiments with people, and even with a very simple robot, people really enjoyed it because it's fun, right? So you move something, and then the robot imitates the movement that you created. This is exactly how we want to do it. Even, you know, kids. And as you can see here, they did it collaboratively, right? So each one is controlling a different limb, and then the robot does the movement together, right? So yet again, we're sort of combining what's, you know, easy for humans to do and what's easy for computer to do. Here are some animations created, right, for different types of robots, right? This is a rather simple ones. Here's some other ones. And then I think I'm going to show you this example of all the movements created by various people. There's some music playing in the background that you don't hear, but that was the idea. Basically, make the robot dance, right? And these are the dances that people made them. So rather simple, rather fun, and again, something very simple for a human to do. So to summarize, basically, all the examples I've shown you, we were trying to use the computer as a new tool to enhance the human abilities in terms of expressiveness and creativity. And maybe the key idea is try to make things simpler by partitioning it to what is difficult, meaning what is difficult for the human being to do, and then let maybe the computer do that, and what is difficult for the computer to do, and get help from the human to do that. So you have human beings that understand semantics much better, can, you know, do those high-level tasks, and then the machine usually does computation much better, can find precise positioning or precise size, you know, much better, can solve optimization problem fast, and basically the combination between those two things can create, hopefully, the right tools for creating those various tasks. These are just the different papers I've been describing, and as I've told you, this is a collaboration with, you know, numerous people. Of course, it's, you know, many of my students and many of my colleagues' work as well. So making things simpler, basically, right? This is my talk, and I'll be happy to get some questions. You can find more details here in my website. Thank you.